look at the proof of de Moivre's theorem. Pardon me if I have pronounced it wrong, but I'm going to spell it out for you, and you can definitely check on the internet how this is pronounced. But for now, bear with me when I say it's de Moivre's theorem, and it has to do something with complex numbers. Okay, so let me remind you what we did till now. We have learned that complex numbers can be expressed in two formats. One was the Cartesian form, where A is the real part and B is the imaginary part of the number, and complex numbers could also be expressed in the polar form, where it is written as r theta, and r is nothing but the modulus of the complex number, which is square root of real part square plus imaginary part square, and theta is the argument of the complex number, which is tan inverse of b by a. This is what we have understood till now, and we have also worked with operations with complex numbers: addition, subtraction, multiplication and division. We'll now move ahead and see what else is applicable, what rules are applicable specific for complex numbers. And the proof here that we are working with is that cos theta plus I sin theta. What format is this number in? It's in the Cartesian form, where the real part is cos theta and the imaginary part is sin theta. One interesting thing to note is that this also immediately gives us the modulus and the argument immediately, that r is 1 here, the modulus, because cos square theta plus sin square theta is 1, and the argument is theta, because tan inverse of sin theta upon cos theta will be tan inverse of tan theta, which is theta, right? So argument is theta and modulus is 1. Now the proof says cos theta plus I sin theta raised to n. So you may think of it as a binomial expansion format, where there are two terms and raised to n, but that's not what we are looking at. This is equal to cos n theta plus I sin n theta. This proof needs you to know a bit of trigonometry. So in case you are not fully understanding the proof, for now you can accept the result, and then over time when you come to the chapter of trigonometry, you will fully understand where this rule is coming from. I'll be using a proof by mathematical induction, because that's something we have done in unit 1, correct? So by now everybody is familiar with the process or the format of doing this proof, and so we will use that. So how do we do that? We start with n equal to 1 or 2 or any specific number, right? So for n equal to 1, the LHS will be cos theta plus I sin theta raised to 1, and the RHS will be cos theta plus I sin theta. Definitely they are equal, so LHS is equal to RHS, so the result is true for n equal to 1. Okay, and now we are going to say, we'll assume it is true for n equal to k. So according to the rule, it says cos theta plus I sin theta raised to k must be equal to cos k theta plus I sin k theta. That's what the theorem says, and I'm assuming it is true for n equal to k. Now using this, I'm going to find out what happens for n equal to k plus 1, and here I'm going to do LHS equal to, again let me warn you, this proof assumes that you know some identities in trigonometry. In case you don't, then you can revisit this unit when you have learned that part of trigonometry. So LHS is cos theta plus I sin theta raised to k plus 1, and I'm going to rewrite this as cos theta plus I sin theta raised to k times cos theta plus I sin theta, isn't it? That's by laws of indices, that when I'm multiplying and the base is same, the indices get multiplied. So do I already know the rule for cos theta plus I sin theta raised to k? Yes. I have assumed that this is equal to cos k theta plus I sin k theta and times cos theta plus I sin theta. Okay, and now I'm going to multiply. So each term of the first bracket gets multiplied with each term of the second bracket, distributive law. So cos k theta times cos theta minus, because I times I is I square, sin k theta times sin theta. That's one term. These are the, why did I multiply this first? Because both of these are the real terms. Plus I times, now let's look at the I terms. Sin k theta times cos theta plus cos k theta times sin theta. So the imaginary terms and the real terms I separated and put them. Now according to the sum of angles identity, cos A cos B minus sin A sin B is equal to cos of A plus B. Okay. So this term here, let me keep this highlighted so that you are able to know why I have used this rule. This term, the first real term, now becomes cos of k theta plus theta because it's A plus B. Similarly, there is a second rule. Okay, the rule is sin A cos B plus cos A sin B is equal to sine of A plus B. Okay. Don't worry about the gap between that. Just this is cos of A plus B and this is sine of A plus B. Let me keep this also highlighted. So what about my second term here? My imaginary part therefore becomes plus I times sine of k theta plus theta, okay, which is equal to cos of k plus 1 times theta plus I sine of k plus 1 times theta. Oh well, this is equal to the RHS. That's what the expression would have been. That means I have proved it true for n equal to k plus 1 also, and therefore the rule is true. So what is the rule really? So I have proved that cos theta plus I sin theta raised to k or n, basically let me write it out n because I proved it for all values of n, is cos n theta plus I sin n theta. This is true for n as positive integers. It is true for n belonging to rational numbers like these fractions, and it is also true for negative integers. So let me give you an example. For example, if it's cos theta plus I sin theta raised to minus 2, then I can very well write it as cos of minus 2 theta plus I sin of minus 2 theta. And cos of negative theta is same as cos theta, whereas sine of negative angle is minus sine of angle. Again, all this needs you to know trigonometry, like I said, but I'm just reiterating the rule for now. Similarly, if I had a fraction, for example, cos I theta plus I sin theta raised to 1/3, if I have, then the rule applies here also. It will become cos of theta divided by 3 plus I sin of theta divided by 3. There will be places where you will get to prove this. So you don't have to blindly accept it. But for now, I am giving you the rule and we will be using these rules for different problems, and I am going to look at one of the problems for you. So I am saying that I have a complex number. So let me change the color so you know how I am using this rule. Z is equal to 1. Okay. Now Z is a complex number, remember. So Z is not just a magnitude, it also has an angle. But what is the angle? Well, z could be cos of 2 pi k plus I sine of 2 pi k. What is 2 pi k? All integer multiples. So k belongs to integers. All integer multiples of 2 pi will have cos 2 pi as 1 and sine 2 pi as 0. So z will be 1. If I had to find the square root of this number, okay, so z raised to half. Let me show you how de Moivre's theorem is useful. So cos 2 pi k plus I sine 2 pi k raised to half, and as per the de Moivre's theorem, the index gets multiplied with the angle, so it becomes cos of pi k plus I sine of pi k. What value can k take? Well, k can be 0 for example, and then what will I get the square root as? Cos of 0, which is 1, and sine of 0 is 0, so I'll get this as 1. What if k is 1? Well, I'll get then z2 as cos of pi, which is minus 1, and sine of 0. What if k is 2? Well, then again I'll get it as cos of 2 pi and sine of 2 pi, so I'll again get 1, and when it is 3 pi I'll get minus 1, and so on, so it will repeat. So plus 1 and minus 1 are the two answers for the square root, which with an angle. So when I say 1, it has an angle of 0, and when I say minus 1, it has an angle of pi radians. So this is how we use de Moivre's theorem. This is a simple example, you will know more, and that gets us ready to do problems with complex numbers.